Good evening, ladies and gentlemen. My name is Petko, and this is Ratio Presents. Happy New Year to everyone. I want to wish you probably a less sterile 2021. 2020 has been difficult for all of us. People tend now to say that we have learned a lot. But either way, in Bulgarian, we have a tradition of congratulating ourselves for the new year with the saying "За много години," which roughly translates as "We wish you plenty of years ahead." And this seems to be more relevant than ever. Either way, it does feel like we have managed to collectively dodge a bullet here. We faced a global pandemic, a global challenge that ultimately we seems to be at least on a track to resolve, not only thanks to our collective effort, but mostly because of the help of different scientific institutions and medical institutions that have collectively worked to essentially save us all. So going forward, although we have sort of managed to deal with this challenge, there are many challenges still lying ahead. That can affect us not only personally but also globally, and it does seem like we are still going to be relying on these same institutions and mainly on the institution of science to help us deal with these challenges ahead. And speaking of these institutions, now we have gotten used to thanking scientists in 2020 for helping us out to go through this pandemic. And I think that a majority of the public certainly realized the importance of science and of scientific institutions, not only for resolving this specific issue that we have faced, but in helping us shape our future and make it certainly better. Now, today we have organized this event with the help and the support of one of these very important institutions, the European Space Agency. We have worked together on a few events, and hopefully we will continue working in the future with them, exploring different topics related to science and space in particular. Today, this event is also focused on defending ourselves. So we have gotten used to in 2020 again to speak about protection. We wanted to protect ourselves from viruses, protect ourselves from other people, but facing future dangers, one of the real existential threats that we are facing as a humanity really comes from space. Now, previously in our history, we have looked at these celestial bodies with fascination. They have awakened our imaginations. We thought that these were signs from the gods, or we have simply observed them as aesthetically pleasing things to observe. But as we all know, science and knowledge often brings grief. So by knowing more, we suddenly realize that these are not just pretty signs from the skies, but are objects that represent a real danger. And we all know probably the best example of that is when we realized that 65 million years ago, an asteroid hitting Earth wiped out probably one of the most successful lines of species in the history of life, the death of dinosaurs. So we suddenly realized that it is really imminent, and it's not a question of if, it's a question of when we are going to face this threat again in the future. So realizing that, we should be happy to know that there are a lot of scientific institutions working on this problem, on trying to build the defenses that are necessary to protect our planet from future events like this one. And one of these institutions is the European Space Agency. I think it's good to remind all of our viewers that, and we have spoken about this before, that it takes approximately €1 per person per year for every European citizen for the European Space Agency to exist. And it is the most fundamental institution and the most important tool that we have for observing future threats and for studying them and for mitigating the risk of either global warming or forest fires or earthquakes or celestial bodies coming to kill us all. So today we're going to start 2021 again speaking about such a global threat, but this time in the context of protecting ourselves. So today we're going to be speaking with Paolo Martino, who is the principal engineer and the main technical lead for the Hera mission. The Hera mission is part of the Planetary Space Defense program of the European Space Agency, and they're working together with NASA on a very special space mission that intends to test a type of intervention that at some point in the future might prove to be our best weapon against an asteroid strike. So I'm happy to welcome Paolo on the call. Paolo, can you hear me, sir?
Yeah, good evening, Petko. Good evening, everybody.
Good evening. I hope you're feeling well and you're feeling prepared to share what you know about the mission, the specifics and the interesting details surrounding the mission, the preparation, how is it going? And I understand you have a whole presentation for us.
Yeah, absolutely. That would be a pleasure.
All right. So whenever you're ready, Paolo, go ahead.
Okay, there we go. Here is my pleasure to present you what are the activities of the Planetary Defense program at the European Space Agency. So I will start with a very brief and quick introduction, which basically will start from the beginning of the solar system, so several hundred of million years ago. I still will try to keep it quick. When the asteroid, which would be one of the main, let's say, topic of our speech, were created. So it's important to understand more or less what was the situation around here, actually not in a galaxy far, far away, but in this specific galaxy and this specific solar system. So if you can proceed with the video number 1. What you can see is how it is believed that the solar system was created. Basically, there was this cloud, it's called the interstellar medium, which is a cloud of particles of gases and molecules, atoms of metals, of several elements. When an external perturbation, which might be something else happening in the galaxy, start to move the equilibrium, and then these particles start to move around and the effect of gravity starts to kick in. Then you get all these particles to start and create a kind of agglomeration in the center, and this grows bigger and bigger and becomes a kind of, we can call it a cosmic vacuum cleaner in a simple way. And this starts to attract all the particles from this cloud of interstellar medium. When this agglomerate reaches a critical mass, it turns into a star. So you start to have nuclear processes inside it. Basically, nuclear fusion is what happens there. And you kind of have a star turning on. When the star turns on, you actually have the very opposite effect. So rather than attracting everything from all around, you start to have this kind of big nuclear reactor in the middle that generates this wind, this radiation, that particle that start pushing things away. In all this, in this environment, then you have all these cloud of element that start to agglomerate in smaller elements, and they can start to create the planets. So if you are far away enough from the central star, you can have local agglomerates that then become the planets. So you have first the big planets, like the gas planets like Jupiter, Saturn, and so on. And then later on, you have in the inner part the one of the rocky planet, because this nuclear, this solar wind has pushed away the gas from the center, so it was more towards the sides of the solar system, and what was left in the middle was mainly rocks, and that's what creates the rocky planets. Asteroids have a similar history. In fact, asteroids basically are mostly the leftover of this planet process, or this planet formation process, which didn't manage to converge into one of these main planets, or let's say were too disturbed by other big bodies to get into a planet. And for example, between Sun and Jupiter, that's why you have most of them, because they're kind of stuck in between the gravity fields of Jupiter and the Sun. In the outer layer of the solar system, it was very cold, and you had mainly actually ice. So the small bodies that remain there are what we know as comets, and that populate the outer region of the solar system. Instead, these leftover, let's say, that were more in the inner part of the solar system, where it was too warm for ice to survive, are mainly based on metals or rocks or carbon, and this is what we call as asteroid. So we already find out that basically asteroid and comets are very, very close relatives. There are three main families of asteroid, and those are classified mainly because of their composition. Okay, so we have the most common, which is a C-type that comes from carbon. It's more than 75% of the asteroid, and those are extremely dark. So what you see here is a picture of the Ryugu asteroid, which is the one that was recently visited by the Hayabusa 2 mission from Japan. But this is a picture in which the light and the contrast has been increased 1,000 of times. The raw format of this picture is basically a black objects on a black background. Those are extremely dark. It's like a piece of coal floating in space. Then we have the S-type silicaceous. Basically, those are rock asteroids. Those are easier to observe because they're not so dark, so they reflect a bit more. They reflect a bit more light, and it's slightly easier to see them. You can see that there are much less asteroids of this category, but they're important for us because most of the asteroids that we call the NEA, so near Earth asteroid, are of this category. So we will see that this is the most interesting for us. And what you see here as an example is a Itokawa asteroid, which is the one that was visited by Hayabusa 1, again, a Japanese mission. Last but not least, then we have the M-type or metallic. Those are still fairly bright, and they're the most common ones in the medium belt. So let's say in the main asteroid belt, the famous one between Mars and Jupiter, we have a lot of C-type. Then in the middle, we have a lot of these metallic ones, and in the inner part, we have more of the S-type, the rocky ones. The M-type might be very interesting, for example, for future resources utilization, asteroid minings, and all this kind of, let's say, innovative ideas that are popping up in these days. You might think then that we know asteroids very well. Actually, this is not fully the case because we didn't manage to visit a lot of them yet. Actually, what you see here, with the exception of Ryugu and Bennu, which were really fresh, are all the asteroids that have been visited so far. So the very big one of the best picture we have for an asteroid, is comes from a flyby. It is Lutetia, and it's a picture taken from the ESA mission Rosetta on his way to the comet Churyumov-Gerasimenko. And this is an example of M-type. So this is mainly metallic. You see the appearance is slightly smoother, but it still has a, let's say, a rocky-like aspect. It's not that you have to imagine an iron ball in the middle of the sky. It's really a matter of main composition. So we mentioned before NEAs, and we see that S-type, so rocky ones, are the most common NEAs. What is an NEA then? Near Earth asteroid or near Earth object. This means it's an asteroid that has an orbit that potentially crosses the one of the Earth. potentially crosses or gets very close by. We will see that even if you get close by, you can still be a bit dangerous because it's not, let's say, it's not that easy to predict the orbit of an asteroid. There are many. How many they are? If we see a graphical representation, this might be quite scary. And here is an example. So you see, this is all the asteroids currently known that have an orbit that crosses the path of the one of the Earth. And we are talking about order of magnitude of 30,000 asteroids. Of course, these objects are the one known, but there are many that we don't know yet. And we'll see in a second whether we need to worry or not. Hopefully not. We'll see. Because you see, it's really crowded out there. So we might ask ourselves, do we ever actually have impacts? Like, is it a real danger, or it's actually the cosmos is so big that even if in this drawing it looks crowded, actually there's so much space that the probability of hitting each other is really low. Well, we have several examples that this is a very, very likely phenomenon. And we don't have to go very far away to see that. We just need to watch the moon. We can do it pretty easy. Actually, the moon surface is covered with impact craters. And this is mainly due to the fact that the moon doesn't have an atmosphere protecting her from the smaller object. So what you can see here is that even really small asteroids, we can call it meteorites, can hit the surface and generate craters. With an atmosphere, on one side, we are in a much better position. On the other hand, we have a series of issues as well. Okay, the first one is, luckily, when we have very small bodies hitting the Earth, we just have actually some kind of firework, something really nice, what we call a shooting star, when we have an object in the order of a few centimeters. But when the diameter grows, you don't need a huge asteroid to make very big damage, because when you start to have an asteroid in the order of 15, 20 meters, you start to have something like this. This is one of the best preserved meteor impact crater. Actually, it's in the United States. And actually, the place itself has been called Meteor Crater, so you cannot miss it. And just to give you a bit more insight and a better understanding of the impressive size of this, and also to show you our commitment to actually certify that this was indeed an impressive crater. This is the same picture in scale with myself during my honeymoon. In case you are wondering, yes, my wife didn't leave me after I brought her to see just a meteor crater during my honeymoon, but you definitely need to find a partner which has the same passion you have, or that loves you a lot for this. And this was already 15, 20 meters maybe. When you start to have something a bit bigger, 25 to 30 meters, you can have something like this. Next video, please. Video 2. Okay, this might be quite famous as well, because it is happening in more recent times. This is the Chelyabinsk accident, we can call it, where again another 20-25 meter diameter asteroid impacted the Earth, and actually this was a rocky one. You have to understand that in this case, the asteroid didn't even made it to the ground, and a lot of damage was done by just basically the shock wave of the asteroid getting warmer and warmer, entering the atmosphere at a very high speed. So you might think, you commonly believe that being hit by an asteroid means just walking on the street and having a physical rock actually hitting you while you pass by. Luckily enough, this is not the likely scenario, or this is not the real danger of an asteroid. The dangerous part is that what you've seen here is something that is comparable to a natural disaster like a typhoon or an explosion of a bomb. In particular, some asteroids, not to mention the Chicxulub, which is one of the dinosaurs, but asteroids can have let's say, the same shockwave and the same explosive power of not only a nuclear bomb, but even a hydrogen bomb, or many more times those. Actually, an impact from the asteroid can release more energy than the most powerful bomb ever detonated on Earth, which is the Russian Tsar bomb. How often does this happen? Fortunately, not too often. But when we look at the Earth, we can actually recognize a lot of impact structures. So what you see now in the map is all the places on Earth where you can definitely identify the shape of a crater and the fact that at some point in the history of the Earth, an asteroid hit the surface of our planet. Of course, you see the smaller and the bigger one. You can clearly identify the bigger one, which are the, okay, maybe not clearly because the map is fairly small, but you all know in Yucatan, you have the one that is believed to be the dinosaur one. And in the, let's say, upper part of Siberia, you have the Tunguska one, which is another pretty famous because it was at the end of the 19th century. And it was, again, a very large asteroid that wiped out a huge area. How many asteroids are we talking about? Tens, thousand, million. First of all, we have to understand that the asteroid follows some kind of, let's say, it's not a probabilistic distribution, but not to go into engineering terms, but the basic concept is that there are few very big asteroids, and the smaller they become, the more numerous they become. So we have really a lot of small asteroids, which fortunately are not dangerous, and a very limited number of big asteroids. So the most famous one is Ceres, which is almost 1,000 kilometer diameter. That's, let's say, I think Ceres will be not very happy of being called an asteroid. I think it would prefer to be called a planet. Here is a bit of summary, in a way, of what are, let's say, the danger with respect to the size of the asteroid. The Chelyabinsk one, which is one of the video we've seen before, we can already see that released a power which was already much higher than the one of the Hiroshima nuclear bomb. Now, it's not comparable one-to-one. Of course, fortunately, asteroids do not have radiation. But in terms of blast, the effect is really similar. And the Chelyabinsk asteroid, despite being just around 20 meters, was already much more powerful than the Hiroshima bomb. In fact, the lucky point was that it exploded in the atmosphere over a fairly low density population region. It was in this area, this remote area in Siberia. And still you had more than 1,000 people injured just by the shockwave that, for example, shattered the glasses of the windows or shattered the cars. So luckily, no casualties, but a lot of injuries. If the same would have happened over a densely populated city, for example, the effect could have been already much worse. Then you see that as you grow in size, the power increases. So the dinosaur Meteor, the Chicxulub, is believed to be 10 to 15 kilometers in diameter and has an estimated power of 100 million megaton. So the Hiroshima bomb, 15 kiloton. The Chicxulub asteroid, 100 million megaton. I mean, it's an energy that the man cannot produce on Earth in an artificial way. It's something difficult to understand for our mind. So This looks like a good news or a bad news. We'll see. Such a big asteroid, as we've seen before, have two important characteristics. The first one, there are not many. The second one is they're big. What does it mean? That they are easy to see. And in fact, what you can see in the lower part of this infographic is that on the right side, the very big asteroid, they are all known. So we know them, we know where they are, we know where they go, and we can predict fairly well where they will go. So at the moment, they do not represent a threat because we know them and we are able to see that there is no risk in the short time that they will impact the Earth. On the other hand, left hand, there are the very small one. This very small one hit the Earth quite often and are almost impossible to see. So you see, I read it for you. We know 3,000 to 4,000. We estimate to be there 4 million. That's the order of magnitude. What is the good news here? They hit us continuously, but they are so small, they never make it to the ground. They can never make damage. So where does the danger lie? The real danger lies in between. So we're talking about this, let's say, central part, this asteroid between around 100-meter diameter. Why? Because they're too small to be easy to see, but they are big enough to make a lot of damage. Between 100 and 500-meter diameter, you can go from create damage on a regional scale, for example, a whole city, a whole big city like Paris, Rome, or London, to damage on a whole region. And a whole region, I mean, thousands and thousands of square kilometers, something as big as the Netherlands, for example, or as big as Italy, or as big as a full Balkanic peninsula, actually, with just a 400 or 500-meter asteroid. This, therefore, is the primary focus of our program, because, let's say, it's not frequent, but it's not as unlikely as a very big one. Because Chicxulub-like, dinosaurs-like, thousands of kilometers is something that happens every millions of years. But something like 100 meters is something that happens in the order of hundreds of years. So as the same, let's say, the same probability of happening of a major volcanic eruption or a particularly severe flood or tornado, but unlikely these other unfortunate natural catastrophes I just mentioned. This is one of the few, or maybe the only at the moment, natural threat that we can actively predict and avoid. So this is the main focus for us, is the study of this category of asteroid, so roughly 100 meters, and of the way to, let's say, do something in case we find out it's a danger. How do we do? We do it at ESA inside one of the newest program of the agency, which is called Space Safety and Security is a full name. It was created last year. And it is mainly based on three categories. It's a program that deals with the safety of the infrastructure in space, of the spacecrafts in orbit, and of the planet from external threats like asteroids. So concerning the space debris, under this new program, ESA is working on a mission for active debris removal. What you see here is an artist concept, is a current concept of the mission, which is something to address the growing issue of, let's say, we can call it the overcrowded region of space, where we might have debris coming from unused parts of launcher or explosion of satellites, any kind of debris which is making space too crowded. Then we have the space weather one, which is a way to protect ourselves from another, unfortunately, realistic and important threat, which is the solar flare. So powerful radiation from our sun that can affect, fortunately, it's difficult that they affect life on Earth because we are shielded again. Our planet is helping us with the magnetic field that is shielding us from this. But this can create negative effect on all electronic equipments like satellites in orbit, but also airplanes flying. So it's something that we need to be able to predict and prevent. And this is again an important pillar of this program. And last but not least, of course, the one I like the most, obviously, is a planetary defense program. So we'll see now that we know a bit more the asteroids and the risks they pose, we see what are the steps we can do to study them and prevent any possible risk. So the first step in knowing whether we need to deflect an asteroid or not is, of course, to detect the asteroid. So to detect these asteroids, there are some telescopes called testbed telescopes. What is the main issue? When we have the usual scientific telescopes, their aim is to, we can say, make a very small portion of the sky bigger and bigger and bigger. So their field of view is very narrow. When you look for asteroids, actually, you have no clue where you have to look at, because you have to try and survey all the sky in order to find if there are asteroids and where they are, because unfortunately, they don't give you a phone call in advance when they pass by. So we had to develop this new type of telescopes, which are called fly eye, like the eyes of a fly, that are basically a combination of different telescopes that allow to have a telescope with a very wide field of view that can keep under control a big portion of the sky, and therefore allow to identify asteroids more easily. Then all this information is managed and analyzed in what is called at AIDA NEOCC, which is Near Earth Object Coordination Center, which is where all these data are analyzed and the asteroid characteristics are then calculated, and also therefore the orbit and whether it poses a risk, a threat or not. Actually, you see here just a snapshot. This is a site which actually is open to everybody. So in case somebody is going to ask whether there is anything secret at ESA, there is not. This is the NEO, the NEA studies, the space situational awareness, is really open to the public. Actually, on the other hand, let's say everybody in principle can contribute. And by visiting this website, you can check all the current asteroids known, their characteristics, and what is believed to be a risk list. Now, when you see a risk list, you don't have to believe that this means there are 1,000 asteroids that are going to hit the Earth anytime soon. There are 1,000 asteroids which have a potential risk of impacting the Earth, which is not completely negligible. Therefore, we need to keep them under control and under more specific control with respect to others, which instead we are sure will not be a problem at all. So as I was mentioning, to detect these asteroids, you need to survey as much sky as you can, and the best way is these so-called fly eye telescopes. There was one already developed and installed by ESA in Sicily, in Italy, which is undergoing testing and will soon be fully operational. And then there will be a second one in the full hemisphere. We are planning to let's say, develop a full network. However, still this will not be enough. The next step here, especially to observe the asteroid coming from the so-called night side, basically if they come from the same direction of the sun, they have the sun behind them, they're not illuminated. So it's really difficult to see such a small object. In order to do so, you need the space-based telescope. So what has been studied, what is being studied both at NASA and ESA, are space observatories, so space telescopes that can actually complete this survey. When we see something with the telescopes, is it easy to find an asteroid? Not that much, because you need advanced techniques to be able to analyze the images and be able to understand what is an asteroid, if there is an asteroid, which one it is and where is it going. Now, this was supposed maybe to be, a GIF would be more clear, but from this static picture, actually, I could challenge everybody online now to tell me which one is the asteroid in this picture. Okay, so maybe just try to tap the right point in the screen with your finger, and let's see if you got the red circle. 3, 2, 1. I bet not many of you got it right, because that was really difficult to spot. But of course, all the big marks are actually the stars that are moving, and this really faint point is an asteroid which is moving in a different direction with respect to the star. So once we find them, it can be done from ground with this fly-eye telescope and in space with future space-based telescopes. Then we assess the threat, as we just see. We have this NEO coordination center. Then what do we do? Let's say that I get a phone call from NEOCC that is telling me, look, there is this asteroid which has a really non-negligible probability to hit the Earth, maybe 1%, maybe 2%. It sounds low, but it's still very high if the potential damage is as big as we've seen before. So we're talking about tornadoes, earthquakes, volcanic eruption. If there is a 1% or 2% or 5% probability that this will happen, do we want to do something to make sure this 5% becomes a 0.0000? Of course we want, and this can be done only in space. So what do? We call them. No, we don't call them anymore. Well, actually, I realized this, which is often the benchmark in terms of asteroid movies, starts to have aged quite a bit. In the meantime, new techniques have been developed, and a question I get often is whether the technique they use there is something that would be feasible. Unfortunately, in real life, well, unfortunately for them, in real life, the people that work on deflecting asteroids are much more beautiful and charming, and work on quite different techniques that you see summarized in this slide. So indeed, nuclear, like in the Armageddon movie, is indeed an option, but is an option nobody would like to use, and that is a last resort only for really, really, really big asteroids, and if you really, really have no time. We have seen that it's almost impossible that we will need that, because such big asteroids are easy to spot. We know where they are. They are not in a collision trajectory with the Earth. But for example, we have to remember that if we destroy an asteroid with a nuclear weapon, it's not that we're going to turn it into dust. We will crush it into a much smaller asteroid. Many of them will still hit the Earth, and on top of being asteroids with the shockwave we've seen before, they will be radioactive. So I'm not sure the outcome will be exactly the positive outcome we like. The international scientific community, which is meeting every second year in a conference called Planetary Defense Conference, actually had worked out that the two most promising techniques are indeed, depending on the size of the asteroid and how much time you have, are those two, the kinetic impactor and the gravity tractor. Now, the gravity tractor means basically using the gravity of a spacecraft that you put in orbit very close to the asteroid, and this very tiny attraction over a long period of time is going to slightly deviate the asteroid and put it on a safe course. The most common instead, in case you have a shorter warning time, a few years, is a kinetic impactor. The name is complex, but the concept is very simple. It's like playing a cosmic pool. So you hit this asteroid with an object, which basically is a spacecraft, as fast as you can, as powerfully as you can, in order to deflect it from its trajectory. You see, I mean, a spacecraft, even if it goes very fast, it's still fairly small with respect to an asteroid. Is that enough? Well, if this fast is fast enough, you can move it a tiny bit, but that tiny bit, if you do it in the right point and at the right moment, is more than enough to move the asteroid of thousands and thousands of kilometers in the other part of the orbit where you would have crossed the Earth. So in this sense, if done in the right moment and at the right place, even a tiny nudge can actually decrease this probability of an asteroid hitting the Earth from a percentage to 0. How are we going to do it? In ESA, actually, we are working on an international cooperation with NASA, which is called AIDA. AIDA stands for Asteroid Impact and Deflection Assessment, which basically means we are going to try and deflect an asteroid of a size which is potentially dangerous. The asteroid itself is not dangerous, but the size is fully representative of what we just seen of possible threats, so 150 meter diameter. This is in a nutshell the concept of the AIDA international cooperation. So we have a NASA spacecraft, which is called DART, together with a small CubeSat called LICHA-CUBE, which is hitting this Dimorphos, it's called, is the moon of a binary system. We see in a second a bit more about why we chose this. One of the reasons we chose this is that we've seen this impact is really small. Okay. When you hit an asteroid which is on its course around the sun, if you change its period by 2 minutes, but its period is 1 year, 2 years, is something very difficult to measure. The elegance of this target, a binary asteroid, is that this Dimorphos rock is rotating around the Didymos asteroid with a period of 12 hours. In this way, if you hit it well, what we expect is to be able to deflect it, let's say to change the period by roughly 8 order of magnitude of 10 minutes, let's say. 8 minutes is already a relevant percentage, and it's something you can observe from ground. So you can actually see whether we manage to move it or not. The basic concept, therefore, is this. The NASA spacecraft, DART, which is launching next year, is going to crash into this Dimorphos at almost 7 kilometers per second. So it's extremely high speed. The mass of the satellite is several hundred kilos, between, let's say, slightly less than 1 ton, but it's going at almost 7 kilometers per second. This means it will have enough energy to move the moon and change the orbit of this moon around the Didymos. But then, I mean, the spacecraft, the NASA spacecraft after the impact will not be there anymore to characterize the impact and measure the effect of the impact. This is where ESA joins in with the Hera mission, which is what you see here, which is instead not an impactor, but it's an orbiter. It will leverage a lot on the expertise of Rosetta in terms of rendezvous with small bodies. Hera will rendezvous with the system in 2024 to study the effect of the impact of DART, and basically from yes, we managed to hit an asteroid, it can become yes, we managed to actually validate a planetary defense technique, and yes, we we actually can deflect an asteroid in case of need. So a couple of words about the target. The target is Didymos, is a binary asteroid, which is not hazardous. So it's important to say, this is not an asteroid which is dangerous for the Earth. We are not doing the first test on something potentially dangerous. Didymos is a binary system which has been chosen because as we were mentioning, it's being a binary provides the perfect test bed, because the moon of this system is exactly the size of asteroid we want to deflect. This gives you a bit of perspective of how big, or actually how small, Didymos is, because what you see in the upper left corner is Churyumov-Gerashimienko 67P, which is the comet visited by Rosetta. This is several times smaller, and actually this DD moon, as used to be called, or Dimorphos, is the smallest, will be the smallest asteroid ever visited. So what you see here is a picture of Ryugu, again from Hayabusa 2. We've seen it before. Dimorphos, the moon, is the same size as a boulder you see in the upper part of the picture. So really, this would be the first mission to a binary asteroid and the smallest asteroid ever studied. A couple of words about DART. We already mentioned it, but it will launch next year, and we will impact the moon, Dimorphos, at almost 7 kilometers per second. We have also a quick animation on this. Next video, please. Here you see DART heading towards the moon at an incredibly high speed. And what you see here is very important. So you see this ejecta cloud, which is one of the reasons why we need to get there and study it. Of course, I talked before about cosmic DART. Actually, the name makes quite sense for cosmic pool. But there are a lot of unpredictable effects, which are the ones that actually will determine whether this technique is efficient or not. So we are not, let's say, the overall aim of this mission is not to demonstrate that we can hit an asteroid. Is to demonstrate that if we hit an asteroid, this is actually useful to deviate it and to therefore defend the Earth and protect the planet. Here you have okay, this is a slightly more technical point, but one of the things we need to study is exactly the cloud you've seen before. So when something, the asteroid is hit by the spacecraft, it's not only the transfer of energy there, but you can have this cloud of dust basically acts as a kind of additional propellant and helps pushing the asteroid in the direction you want. So on top of the exchange of energy of the impact, you have this kind of additional thrust given by this cloud of dust that you are ejecting into deep space. So in this case, the efficiency of this process, this is engineering blasphemy, but would basically be higher than 1. So you get an F, this means you get an effect which is better than you were expecting. This is what is currently believed to happen, but it's not sure that it's what will happen. And this is why we need a full-scale demonstration. Another important thing is to understand how in this impact affects the generation of the crater, and how this impact creates different kind of craters depending on the material and depending on the interior structure. So what you see here is 2 different simulations of which kind of crater we are supposed to get depending on the interior structure. All these models are the ones on which the scientists currently base the calculation that tells us, yes, we believe it's possible to deflect an asteroid. But all these have been correlated only to experiment at lab scale, laboratory scale. Of course, you cannot throw something of 1 ton at 7 kilometers per second against something else in a laboratory. So something in the real scale of this has never been done, and this will be why we need to get there and study what's going on and if this works, so that the scientists can correlate the model with the reality, with the real experiment, and understand whether this is an efficient technique and if it will work or not. So hopefully, if everything goes well, if the demonstration is successful, we know we will have in our pocket this technique to deflect potentially dangerous asteroid, and we will be able to use it anytime we need it. Otherwise, we will all have to work again and find new effective techniques to protect us from this threat. Since we are there, since we have, once Hera is there to visit this asteroid for planetary defense purposes, so to do the characterization of the impact and demonstrate the technique, of course, we are also there visiting the smallest asteroid ever visited. So despite not being a purely scientific mission, because this is a mission of the Planetary Defense Program, there is a series of scientific, we call it bonus scientific return that we can achieve by getting there. So the first of all is, of course, understanding the collision space. That's what we were discussing, because you can have different effects soon. Then understanding the geophysics of the small asteroid is very important to understand what we said at the beginning. So understanding the formation of the solar system. We also seen that let's say most of the material became big rocks, then became asteroids, then became bigger planetesimals, then the planetoids, and then planets. That's the scale of how you call rock in space as it grows towards a planet size. And this is a very violent process characterized by a lot of crashes of one into each other, the material melting, violent ejection of stuff that changes significantly the matter and the structure of the things. Most of the asteroids instead have not gone through this process, but are still, let's say, like they were created millions of years ago. So they're kind of time machine of our solar system. Therefore, studying them is extremely interesting from the scientific perspective as well. It's also important to understand that these scale effects at large scale. We've seen before that we believe that when we impact something, we get an ejection of material, but you could actually have the very opposite effect, which is having a shock wave that goes on the other side, and then you have the ejection on the opposite side, and this creates a negative effect. And then this will also be, next video please, the first time we visit a binary asteroid, which is something really mysterious in terms of formation, and it is believed to be, as you've seen in the video, starting from a single asteroid. It starts to spin from a series of effects. It loses some material, and then this material is ejected away, but not too far away, agglomerates again, and then is captured back from the gravity. And this gives to this asteroid this what is called top shape, because of this centrifuge force, which is given by some effect, which are, let's say, it's difficult to believe that they actually can have an impact of the orbit of an asteroid, but it's just basically the different properties of how the surface of the asteroid warms up or how it emits thermal radiation. On either side, instead, what we have there, so our component, to give you a bit more information, is a mission called Hera. And now I will take a quick break and leave the floor to a person which I'm proud to call a colleague, let's say, a quite famous member of the scientific community of the Hera mission, famous astrophysicist and part-time guitarist.
Hera is going to show us things no one's ever seen before. This ESA mission will be humanity's first ever spacecraft to visit a double asteroid, Didymos. This asteroid is typical of the thousands that pose an impact risk to our planet. Imagine a mountain in the sky with another rock about the size of the Great Pyramid swinging around it. That's Didymos. And just the seemingly tiny moon would be big enough to destroy a city if it were to collide with the Earth. But we're going to find out if it's possible to deflect it. This is going to be really, really hard. Aiming at a 160-meter wide target across millions of kilometers of void. Could we stop an asteroid hitting planet Earth? The dinosaurs couldn't, but we humans have the benefit of knowledge and science on our side. Hera is led by a multinational team of scientists and engineers, humanity's makers and doers. Right now, all we have is many years of research and theories, but Hera will revolutionize our understanding of asteroids and how to protect ourselves from them. First, NASA will slam its DART spacecraft into the smaller asteroid at more than 6 kilometers a second. Then ESA comes in. Hera will map the impact crater left by DART and measure the asteroid's mass. Knowing this mass is key to determining what's inside and knowing for certain whether we would be able to deflect it. Next come our briefcase-sized CubeSats. If you think of Hera like an aeroplane, then CubeSats will operate more like drones, able to take more risks, flying closer to the asteroid, carrying state-of-the-art science instruments, eventually touching down. The scale of this experiment is huge. One day these results could be crucial for saving our planet. Hera's up-close observations after DART's impact will help prove whether asteroids can be deflected, prove whether this is an effective planetary defense technique, so that if an asteroid ever poses a real threat to Earth, we'll be ready.
The chance to thank Brian May, which I guess was a guitarist a bit more than part-time, and I hope it was recognized by most of the audience. Honestly, when I gave a presentation to a slightly younger audience, people asked me if it was Sir Isaac Newton. That made me feel very old. I hope it's not the case tonight. So here a quick summary of the Hera mission. Therefore, we said that we need to get there and characterize the impact. Therefore, study the asteroid and study the crater in much detail in order to be able to understand more of this asteroid and understand more of the impact and the effect of the impact of the DART mission, and understand whether this technique can be used or not. We are launching in 2024, and we are getting there after a pretty long cruise, more than 2 years. And why so? The NASA spacecraft actually is going into a collision course, so it gets there very quick. We're talking about a few months. From the orbital mechanics perspective, instead, having a rendezvous with the object is much more difficult. So we need to have a quite long detour in order to get there and manage to get side by side with the asteroid. Once we will get there, we will have a series of phases in which basically we will try to get familiar with the environment and get closer and closer to the asteroid, trying to keep the risk as low as possible, because of course the body is so small that you don't actually orbit around it. You are together in orbit around the sun, and you need to move around in a very delicate way in order to be sure you stick around the asteroid and you do what you want to do. It's like walking on space eggs, we can say. And then it's structured in a way so that at the beginning, let's say we play it safer and we try to achieve most of the mission objectives from a safe perspective and a safe position. And as time goes by, we get closer and closer and try to get more outcomes in a more risky way. We do this with this nice spacecraft, which is this is the current design. Actually, it's just undergone a major ESA review, and I'd be happy to actually address any question on the spacecraft design itself, which is actually my main, let's say, the main area I work on. But say, long story short, is a relatively typical deep space spacecraft with, of course, big solar panels that are visible right away in order to generate powers when you are really far away from the sun. And you see on the upper part of the box, what is called the top deck or asteroid deck, you see a series of instruments. What we have is 2 navigation cameras that would allow us to navigate around the asteroid and take also pictures of the asteroid and of the crater. We have a thermal infrared imager, which would allow us to do 2 things. First of all, to characterize the material of the asteroid, and second, to try navigation techniques. We call it all weather, meaning you can see the asteroid also from the night side, because with a visible camera, of course, in this visual navigation, you just see the part which reflects the light. Instead, with the thermal one, you can actually always see the whole asteroid just because it's warmer than the background. Then we have a laser altimeter, and last but not least, you don't see it from here, but in those 2 below those 2 orange leads, we have host 2 CubeSat named Juventus and Milani. Those are 2 companions 6-unit CubeSat that we will use, let's say, to complement the measurement of Hera. And of course, the CubeSat are a bit more agile and they can take more risk. So we expect them to get closer to the asteroid and try to get even more insights. This is a bit where the asteroid is. So as I was mentioning before, we will have to go very far away. And you see this is the red orbit is one of Hera, and the light blue orbit is one of Didymos. So we need really to make a long way, including a Mars swing by, in order to get in the same place or in the same speed of the asteroid. And once we get there, we do a series of orbits, as I was mentioning. We never actually, we're not in what you can imagine as an orbit around the asteroid, but we do the same technique that was done in Rosetta. So we have this, we are together in orbit around the sun, and we do these arcs, which are hyperbolas, actually. We're doing so from as seen from the asteroid. Hera is doing these hyperbolas, these arcs, and is using advanced navigation techniques to do so. What we use at the beginning is called centroid navigation. So the spacecraft is autonomously capable to identify the asteroid and make sure that we are always pointing the cameras and the instrument towards the asteroid. Then we have a second phase, which is called close observation, where we will do flybys that get as close as 2 kilometers, in which we will still use this system, but at some point, we will get so close that the asteroid feels completely the field of view. At that point, it's very difficult for the onboard systems to understand where you are and where the asteroid is, because you see only asteroid, so you cannot have a precise pointing. And here we start, therefore, with the next step, which is one of the main navigation experiment we have on board, which is called feature tracking. So we have an algorithm on board, which is capable of taking pictures, recognizing features, and understanding the relative motion of the spacecraft with respect to the asteroid by mapping this feature. And here, an example here, this would allow us to get much closer to the asteroid. And of course, the similar techniques are commonly used on Earth in other sectors as well, maybe. But we don't have to forget that this has to run on a computer on the other side of the solar system. So the challenge of this is to make an advanced algorithm, which is actually very light and simple in computational, from a computational perspective. So in conclusion, just to wrap up a bit what we've seen today, is that if the question is, will an asteroid hit the Earth? Yes, the asteroid will hit the Earth with 100% probability. The question is not if, but when. Actually, in addition, is which size. So fortunately, yes, an asteroid will hit the Earth. No, a catastrophic asteroid like the dinosaurs one will not hit the Earth. But yes, a middle-sized asteroid with the capability of doing a lot of damage will hit the Earth in a matter of tens of years or hundreds of years, but not thousands of years, and we need to be prepared for that. For this, the most effective technique which has been studied so far is what we've seen, the kinetic impactor, so crushing a big object, a fast object into it. And in this context, the Hera mission at ESA, together with AIDA, provides, let's say, a robust mean to perform this planetary defense validation test with a good balance between risk and innovation, with lot of technology demonstration that we've seen, and with this incremental approach. And in addition, such a mission allows us to have an, let's say, unique test bed to understand better the formation of the solar system. So yeah, in conclusion, we cannot but agree with the dinosaurs that now is the time to develop the technology to deflect an asteroid. They were just joking about it, but we are actually doing it because we don't want to end up like them. Thank you.
That was really fascinating information. I gotta say though that I'm kind of disappointed that the nuclear option is out the window. You know, it seems like to be the more ape thing to do. You know, to to do it with a bang.
Yes. No. Okay. To be honest, let's say I can share with the writers of the Armageddon movie that indeed, if tomorrow they would tell us, look, there is a huge asteroid that is going to hit us, you don't have to study too much. Everybody thinks everything they have and they just throw it at it. That I understand the reaction.
Right.
Fortunately, that's not the case, because these big asteroids are not a threat. We know where they are. We have to prepare for the smaller ones, where we can use more elegant solution that don't risk the life of people, because as I was mentioning during the presentation, the nuclear solution is really risky in terms of what comes back to the Earth.
Right. I'm going to ask a really probably stupid question, but you did end up with saying that it's very improbable and most unlikely and almost impossible that the same size of asteroid will hit us as the one that killed the dinosaurs. You're saying we know where most of these are, but is a surprise actually possible there? Because it sounds a little bit too optimistic to me. That we observe them all and we know where they are.
Okay, I was referring to asteroids.
Yeah.
There is a small caveat there. Of course, asteroids and these near-Earth objects are not the only object that pass by our solar system. And not so long ago, we had this example of an interstellar object, this Oumuamua,
right,
that caught everybody by surprise.
Yeah.
So we can be fairly confident with our, let's say, neighborhood asteroids, because those we know very well. But for example, interstellar objects like this one, or comets, which come from beyond the visible areas of the solar system, some unlikely event like that could always happen. But in that case, I mean, the probability is as an endless number of digit after the comma, after the zero.
Right, but in case that happens, how much time are we going to have? You know, considering the average speed of you know, of an object like that, let's say.
Well, depending on the characteristics and the speed, we can talk about maybe several weeks, but we are not going to know it years in advance, because from the moment it becomes visible to when it gets there, yeah, the order of magnitude is maybe months, but not years. Yeah.
So will that be sufficient? You know, assuming that this exercise that you guys are now trying, that it succeeds, and and that this becomes the principal technique that we are going to be using in the future. If a scenario, however unlikely it is, happens like that, will these few weeks or a couple of months will be enough to organize a response?
Weeks would be challenging. Months would be okay.
Months will be okay. All right. So, well, obviously, what's most important here is that we notice such an object, and the big question here is: do we have the sufficient infrastructure to ensure that we're going to capture objects like that? Meaning that is there a concerted effort or multiple institutions across the globe that are doing such observations, or it's more fragmentary? Is there a global monitoring system?
So at let's say we don't have yet a really unified system, but there is a lot of coordination. So up to now, let's say the planetary defense effort have been led by NASA, especially because of the, let's say, of the usage of some of the best ground-based telescopes, of course. What ESA has done is to let's say, collaborate significantly and actually help to improve a lot the situation is with this new generation of ground-based telescope, this FlyEye, which allow to image larger portion of the sky at the same moment. And there is a continuous coordination there. So there is, let's say, we don't have yet an ONU-like central database, just because there is not, let's say, it's a matter of collaboration between agencies, but there is a continual exchange of information among the main agencies. And as I was mentioning before, the planetary defense community is, let's say, is cooperating continuously. And this mission is a very good example, because we have a NASA component, from the Italian Space Agency, the ESA component, the Hera mission, and we are embarking an instrument from JAXA, the Japanese agency. So this is already, let's say, a good example of how the big space agency around the world are sensitive to the topic, and we are all working together for this.
Right. Now, we have seen that in most you know, artistic depictions of situations like that, let's say the movie Armageddon, you know, an object is approaching Earth, and this is being kept as a secret, you know, to the you know, global community. You know, governments keep it to themselves because not to panic society, and et cetera, et cetera. Is that actually possible and realistic, you know, to hide such an information, considering, you know, how many observation points you have, and, you know, amateur astronomers and so forth?
Yeah, what we often see in movies also, that the killer comet is discovered by mistake from somebody in the backyard with a Galileo-like telescope.
Of course.
Okay, that level is a bit unrealistic. But okay, first of all, it's realistic that comets and asteroids are spotted by amateur astronomers. And second, as I was showing during the presentation, at ESA, in particular, we have a pretty open data policy for this. All the information we have on the asteroids are publicly available on this portal, which is accessible to everybody. So I mean, it's a topic that is so important that we don't hide anything. On the contrary, as soon as we find something potentially risky, we try to raise awareness on it and share views with everybody around the world to find solutions, because it's let's say, it's very difficult. These asteroids are, especially the small one, are subject to a lot of perturbation when they can be attracted here and there, or even just the effect of the wind from the sun can deflect them a lot because they're very small. So you need a lot of effort and advanced computation technique in order to predict the orbit very well. So it requires a global effort, and we are working on that. So I really don't believe that, let's say, if it was something worth being hidden, it would be impossible to hide it.
Right.
Because you would see it in the sky as bright as the moon.
Yeah, but that doesn't mean that I will understand what I'm seeing necessarily. People are like that. All right, so okay, so it's going to be out there. We're going to be out of toilet paper real quick again. I guess. But at least it's nice to know that we obviously have all the tools necessary at least to detect it on time, and hopefully you guys are successful with the mission, and we can figure out a way to move it. And now, considering these methods that you described, you covered some of them. The kinetic method. Obviously the nuclear option is there. What are some of the other probably more speculative or far-fetched methods that that have been on the table and that have been removed? Because, for example, we have one question from a viewer here. Can we just strap an engine to it and just push it? For example.
Well, that's not such a bad idea. There are indeed some more, I don't want to call it sci-fi, because they all have a scientific background. They're just too complex. Let's say the current technology is not ready yet to have the power needed for that, or something like that. I give you some example. Okay, one, as we said, is this gravity tractor, which means you need to take a big object, get there close to the asteroid, and kind of pull it away just using the force of gravity. But that requires tens and tens of years. Another option was studied was to hit an asteroid with a laser that would kind of move the asteroid also by hitting the surface, or even paint it. This is
I'm sorry, painted.
Yeah, that's correct. Because depending on the color of an asteroid, or any object, depending of the color, can become warmer or colder, or emit more or less radiation. No? You see it quite easily when you leave your car parked in the sun in summer, whether it's a light colored car or a dark colored car. That makes a lot of difference. No?
Right. Yeah.
So the asteroid, we've seen they're really dark, the cold one especially. If you paint it white, you change its temperature so much and its properties so much that it reacts to, let's say, gets a different temperature. And on a cosmic scale, just being warmer or hotter can give you a very small thrust, a very small propulsion, which on a cosmic scale end up in deflecting an asteroid. The problem is having a kind of roll big enough to paint a 200 meters asteroid in space. That's
I was going to ask me, how are you going to do that? Yeah, this seems really, really far-fetched. At the beginning, I thought someone is just going to write something on it. Yeah, it's something. Yeah, also a very human thing to do, to be honest. I don't know. Okay, a couple of more general questions, and then we do have quite a few very specialized questions that I'm not even sure I'll be able to articulate correctly. But we'll get there. So just giving you the heads up. Be ready. So when it comes to building such a defense mechanism, again, let's assume that this works successfully. Now, are there plans, or how do you envision this to go about in terms of deploying the infrastructure that will be necessary to do that? Will that be necessary to be placed on Earth, or are there plans to build it on other celestial bodies, for example, like the Moon?
There is no specific plan like that yet. Say not a concrete one, But what you mentioned is something definitely worth studying. And there is nothing that forces to have this base on Earth. These might as well be. I mean, the ESA and NASA are working now on, let's say, coming back to the moon and beyond with this lunar gateway and so on. So actually. Well, it's not planetary defense; it's moon defense. But this topic of asteroid deflection is important also. Let's say if you want to colonize the moon, you need to make sure you can protect yourself from all the asteroids hitting the moon as well. And there you don't even have an atmosphere. So indeed, it must be a kind of infrastructure which is flexible enough to be deployed on every planet where a man lives. But let's say as a first step, I think it will be just Earth-based, and it doesn't need. Let's say what is difficult at the moment is to demonstrate it works. But then if it works, it should. Say we are working also on something. It sounds absurd, but relatively low cost. So something affordable to have something ready in case of need.
I was going to say, because projects like that do seem to be very expensive, and how do you go about in convincing the public that you're investing so much money in an event that is fairly implausible, to build something like that?
Well, the important thing is to put the things in the correct perspective. So indeed, it's a lot of money. But it's let's say extremely cost efficient with respect to let's say with respect to traditional high performance scientific mission. We try to follow a different approach and try to have a kind of fast track, low cost approach, willing to take a bit more risk, but in order to make it in less time and less money. And what we're talking about, similar to what you mentioned at the beginning, is the mission itself, all inclusive, the satellite, the launch, the operation, and so on, will be less than €1 per ESA member state citizen.
Yes.
So I think it's a fair contribution. If they would ask you €1 to be sure you'll never be hit by an earthquake or a tornado, I'm sure you would consider it.
Yes. Yes. Hopefully, most people think like that. Okay, I just have to ask this question, although it sounds a little bit ridiculous to me, I would say, and I allow myself this comment because I know the person who asked the question. But let's go ahead and just ask it. Can we use this? Can the space debris that we actually have in Earth orbit right now act as a kind of a defense for such celestial objects? I just wanted to see your reaction on this question. What do you think?
The problem is that the most of the space debris is too small for that. So if you get a 20 meters asteroid, it's going to wipe off the space debris and and they are going to come together. Well, actually, it might be funny because when they eat the Earth, then you will find also some, let's say, technological pieces, because maybe you find a piece of the satellite and you think it came with the asteroid and is from an alien civilization. Instead, is from the 70s explosion of the satellite.
Well, your answer went into a direction that I didn't even thought about. But thank you for this image in my head. That sounds cool. Okay, here is a specialized question here. I would assume it's asked by a space engineer, but so just try to follow me here. So, do you consider the actual geometry of the DART spacecraft in the simulations, or you use a projectile with a simplified shape and equivalent kinetic energy?
That's a good question. Okay, I start, of course, put my hands forward. This is that's not really my field of expertise because I'm into designing a spacecraft. This is a really specialized. There is a dedicated team at the scientific community of NASA at APL, which is working on that. But I do believe the problem is that it's so high speed, which I believe a projectile is okay. Like the shape of the spacecraft itself is not going to make any difference at that speed. That would be my personal opinion. But I don't know if there is any mean to do that, but I can surely investigate this and come back with a reply if this makes sense.
From the same gentleman who asked the previous question, so can you tell what approach for estimating Didi Moon's mass will you use, taking into account that Hera spacecraft won't be present at the moment of the DART impact?
Okay, so the mass, it's a binary system. So the mass of the two asteroids together actually can be derived even from ground, from orbital parameters and so on. So this asteroid is passing quite close to the Earth. So we are going to look at it with the most powerful telescopes we have. And in addition, DART, as DART gets close, is going to gather information of it. So we will have the total mass with pretty good accuracy. When we get there with Hera, we will get the additional information that is impossible to get from this distance, which is the split of mass between the Didymos and the Moon. Because from observing how they rotate, you can know the split of the mass and the total mass again. So we can actually know the new total mass and have this additional information that is fundamental for all the models, which the ultimate target is to know the mass of the Moon. So from ground, we know Moon plus main, but we cannot know only the Moon from ground. And with Hera getting there, we're going to get this.
Right. Is there a way, because obviously, the distance to the experiment seems to be an issue, when it comes to how specific the observations can be and how detailed. Couldn't a simulation like that be, sort of designed in near Earth orbit, so to say, to test the concept to an object that is, it could be even artificial. It could be, something that we created, just to test the concept closer to Earth, so it can be, better observed whether this proof of concept actually works.
Well, it's not easy to. I'm not sure it could be done. We have to think about it a bit. But to create such an object artificially would be, I'm quite confident, would be more expensive than doing this, because you need to bring. Well, no, sorry. I'm 100% sure it will be hundreds of times more expensive, because you need to bring all of this material in orbit and then still perform the mission. So this target was, the concept of this concept was actually invented by ESA in the early 2000s. And at the time we were looking for asteroids in orbit around the Earth. After several years of study, this has been recognized by the international community as the best target, because of what we said before, because it passes fairly close to Earth, so you can even see it from Earth. And being a binary, we have the object we are looking for, this 150 meters asteroid, which otherwise it would be very difficult to spot, because as we've seen, those are small, difficult to find, so we would have need to be really lucky to find it.
Right. All right. One more question that is a little bit more specialized, so pay attention here. So what is the size of the numerical models you used? Impact crater size, Didi Moon sized, or binary asteroid sized? Which numerical method do you use, SAIL or SPH?
Okay.
Come on, Paolo, you don't know what SPH is?
my guess is as
it's
good
common
as
knowledge.
Yeah. I think that's again one of these questions of I can find out quickly, but that's really outside of my area. So
all right,
I can spend 10 minutes discussing with him about which kind of thrusters we have on board and how much fuel we need to get there. But this kind of it's more because all these scientific aspects are mainly under the responsibility of the scientific community, which is not something strictly related to the European Space Agency itself.
Right.
It's a big scientific community. For example, the leader of this team is my colleague and friend Patrick Michel, is the director of the Côte d'Azur Observatory in Nice.
Mm-hmm.
Then you have several scientists from all over Europe, from research institutes, from academia. So you have all this community of university professors, students, researchers, right, that are the one working on this simulation, and are the ones that ask us engineers to build something that allows them to prove that they are right.
Right. Okay, so the assumption is that this is information that can be found in the scientific literature.
Yes.
Somewhere there. Right. Okay, so I spoke in my introduction before about how crazy 2020 was, and one of the more memorable events was the loss of the Arecibo Observatory. And it was a quite sad moment for all of us, I think. The question here is: does the loss of of such an important scientific instrument, although the loss is very symbolic, but at the same time it's in practical terms it's also a loss for the scientific community. So does the loss of the Arecibo Observatory actually impact our capabilities in terms of observation of the sky?
Well, to give you an example, in my presentation at some point there was a slide that was presenting Didymos, and there was a very faint image, kind of. It looked almost like the television white noise. It was difficult to understand, but this was an image of Didymos taken by Arecibo. So. Wow. We were directly affected by this as a mission. So let's say there are projects for new developments all over the world, not only in the States and in Europe, but also I
think in China is the biggest one right now.
Yep, that's correct. So let's say the world scientific community will still have tools available for this, but of course everybody had a piece of heart in Arecibo, even outside of the scientific community. Just watching any sci-fi movie, at some point you always get to know this amazing site that has contributed so much to the advancement of the knowledge of the universe as we know it.
Yes, as a memory dedication to the Arecibo telescope, I watched GoldenEye the other day. That was my Christmas movie. So that was really cool. All right, I actually want to show one video that we have. Well, we haven't prepared it. We found it on YouTube, like most people do. But I think you've seen this one, and I would kindly ask you to comment while the video is going. It's the comparison of different asteroids that we have. So if the technical team, we can see it now. I think it's a really cool video, so I just wanted to show it to people. So,
yep. Okay, this is going to be a nice firework. And this starts to be like the Chelyabinsk one that we said. We are in this ballpark. So something like this is already giving you a nice blast.
Right.
That's the notorious Apophis and 370 meter. This is already going to blow up a whole region.
So is the Apophis actually the most dangerous asteroid that we have out there?
That is one of the most dangerous we know of, but it's still fairly not dangerous.
Okay.
We are more worried of the one we don't know than of the one we know. That's it.
Fair.
We go to Castalia. So Castalia, it's already dangerous on a nationwide scale. But even bigger. Here we start to get close actually to Chicxulub, the one of the dinosaurs. So actually, yes, I think the one below should be Manhattan in New York City. So you think that this Eros is going to wipe out Manhattan. Well, actually not. Eros is going, say, AIDA and Eros have the potential to wipe out half of Europe, I would say.
Phew. And all life on Earth with it, right? I mean, an impact like that will actually, cause, changes in the climate and all the things that we know about the
Yes,
dinosaurs. Yeah.
there is yes, there is a bit of course, debate in the scientific community on what is the exact critical size and critical energy, but it's around there. So, well, okay, here we are talking about asteroid that will definitely, they will not just say be dangerous for the life on Earth, but they will completely change the shape and appearance of the Earth.
Now
Okay,
here is a
Europa is a
question.
moon from Jupiter.
Right. Is
It's an
there a
asteroid
reason why we gave feminine names to all of these? It's the same like hurricanes. What is the convention here?
I don't know. Well, okay, so Pallas Vesta, and now we have Ceres, I guess,
Yes,
coming. No,
thank God.
Ceres, okay. Yeah, with the, okay, Ceres is going to basically split the Earth in two or something like that, most likely.
Right.
I
Right,
think
so
at
yeah.
the beginning, well, the first asteroid actually were discovered very, very early in the history of our civilization. So at the beginning, they had the name of Greek goddesses or something like that.
Right.
So maybe the first one come from an age in which they were maybe related to goddesses of wrath or of, well, maybe at the beginning, good goddess, and then once I found out could be dangerous, they changed to maybe feared goddesses. But I can tell you that they nowadays it's not true anymore. Like the ancient have this goddess name, but now there are several asteroids named after colleagues and scientists or people who discovered them. So
Yeah.
so everybody might have in their life, if I don't know exactly how to get there, but it's possible to get an asteroid named after you if you have been a key player in the asteroid community.
It will be really cool if you're the person who discovers, this surprising object that comes and nobody have seen, and it ultimately destroys Earth and it carries your name. That will suck.
Okay, there will be nobody to know it, so it's fine.
Right. All right. A quick question regarding these missions that we the very successful missions Hayabusa and Osiris Rex that have brought samples from asteroids. Now, how does the scientific information gathered from this mission help you guys in terms of planetary defense and space safety?
Well, let's say we started a bit the presentation by showing all the asteroids we visited so far, and we've seen there are really not many. Yeah. So any additional information we get on those asteroids, it's a giant step forward in our knowledge of these bodies, because all the information I presented is the current best knowledge of asteroids, but there are so many things we don't know yet. We don't know, let's say, how exactly are they inside, how they behave if you nudge them, which are all the materials that constitute them. Like we can make assumption on most of the composition of the asteroid based on traditional methods, like the kind of light, how they reflect light, or which kind of radiation they emit, let's say, wavelength but we really don't have a lot of information about their structure, their texture. One of the main experiments of Hera actually would be to bring a low frequency radar, which is something that is able to scan the interior of the asteroid. That will be the first time that this is performed, and will help a lot to understand whether we can deflect it with this impact or not. Because if it's all, let's say, a conglomerate of rocks, but it's empty, it's going to absorb a lot of energy.
So it's, yeah.
We'll see.
We'll see. We'll see. So speaking of future trends, we are now seeing, at least in the public sphere, it becomes obvious that there are lots of private and state players actually who are in the game of asteroid mining. They're testing it as a concept. Now, you as a person who studies asteroids really closely, what is your assessment here in terms of, let's say, time scale? I mean, how far-fetched is the idea of mining asteroids for resources and making it in a way that actually turns a profit?
That would require a lot of studies, because I'm sure that all the let's say the main private actors we all have in mind are already doing that and have already done that. And if they haven't launched anything yet, it means they maybe haven't reached the break-even point yet.
Yeah.
Because it's pretty similar. And the Hayabusa or the Hera technology, it's all there is a lot of cross-talk in there. So you need the technology to find an asteroid, to get there, but not crash into it, get close by, possibly land or operate very close. Take something, but take enough material that tells you it's worthy to get there, because I don't remember the exact figure, but in all this sample return mission, we are talking about tens of grams, maybe 100 grams, half a kilo. But even if it was
kryptonite, for example,
yeah,
it has to be kryptonite, to be worth it. I don't know.
Yes. So, but for half a kilo of kryptonite, you have to put together a mission that maybe costs hundreds and hundreds of $1 million or million euros. We'll get there. I'm pretty confident. I don't know how quick. What I know is that mission like this one will help further develop the technology that will be also used for activity like asteroid mining.
Right. All right. So putting aside the fact that you're working on the Hera project and it's sort of your baby, so you have a natural preference, of paying most attention to that. But which is the other European Space Agency mission that you are most fond of and you're most interested in and you're closely observing? I mean, what interests you in terms of what your colleagues are doing in the Space Agency at this moment?
I guess currently or in the future, because if you look at the past, of course, it would be my Rosetta, and the mother or grandmother of Hera. Okay, I will give. Okay, it's difficult. That's really a terrible question. It's like picking up your favorite kid, I guess.
Yeah, I put you on the spot here. You're going to have conversations with your colleagues afterwards, but go ahead and answer.
They're all extremely important. Say, of course, the one of a topic which is, let's say, closer to the passion for exploration. If you're interested into this inspirational aspect, there are a lot of mission ongoing to further explore the solar system, both with man and without man. I mentioned before the lunar gateway, but also let's say getting to Mars and bringing back samples to Mars. That is amazing in terms of let's say expanding our universe, our horizon, let's say. But okay, it's also true that it's very important also to before getting there to make sure we treat well where we stand, and in this sense we have a huge series of amazing Earth observation satellites that help us understand what's going on Earth and what we can do to make it better, as well as several infrastructures that makes our day-to-day life easier in terms of communication. Okay, it would have been a joke, but I could say one of my favorite programs is a telecommunication program, because I'm a football fan and I like to watch
you would like a better
my team playing.
Right. Okay, well, Paolo, thank you very much for this conversation and for the talk you gave us. I hope that more and more people will realize how important it is that the work that you guys are doing, not only you and your team, but the whole community in the European Space Agency. As an organization, it tends to be not very well understood by the general public in terms of the importance of the projects that you just described. and having in mind that this is a publicly funded institution and that money for science are chronically insufficient, just to say the least. I think it's it's becoming more and more important for the general public to be more, first of all, better informed, and definitely to be more inspired in order to support scientific institutions such as ESA. So again, thank you very much for the work that you are doing. I mean, you guys are watching the sky for us. I will sleep much better tonight knowing that someone is paying attention. Someone is paying attention to that. So I wish you all the success that you can get from this project. I hope that everything goes smoothly, and of course, as is traditional by now, I just wish you health. So stay healthy.
Thank you. And just to be safer, don't sleep too close to the window, just in case.
Thank you, Paolo. Duly noted. Thank you, sir. Thank you.
Thank you.
All right. So I just have a few words to share with our public before we close. First of all, I would like to thank obviously the European Space Agency for giving us this tremendous privilege to have conversations with people like Paolo and to explore such amazing topics, such as the one that we just discussed. So thank you. We thank a lot to the European Space Agency for the support and the cooperation in making this production possible. Obviously, I want to thank Sofia Tech Park for giving us this awesome studio. So thanks to the guys from the Tech Park as well. It's a wonderful facilities here, so check them out. And moving forward, what do we have? We already started the new season, so to say, of our Ratio events. So we will continue with our Ratio Online series at 8 o'clock on the 19th of January. We will explore, again, a scientific topic close to space. So some of the viewers are seeing this in Bulgarian, but we will be discussing essentially the life cycle of a space program. So stay tuned at 8 o'clock on 19th of January. That is traditionally Tuesday again. We will expect you then. And then again, we have one more space topic. So we have a very space-focused month. Not a space-focused month, I'm sorry, a very physics and space-focused month. So we will be speaking about the LIGO experiment, observing gravitational waves. Again, we have an excellent guest that we will be announcing very soon. The date is 26th of January. Again, live stream at 8 o'clock. Moving forward, what else do we have? So if you would like to follow up on all the events that we have made in cooperation with the European Space Agency, we have covered topics like space debris, the different missions to Mars, and topics around Mars exploration. You can check them out at ratio.bg/videos. So if you want to follow up on these, please check them out. These were also awesome events. What else do we have? Of course, we would like to thank to all the people who are supporting this this program and that are supporting Ratio as an organization in general. If you would like to support the popularization of science and help us out in our effort to make science more understandable to people, you can do so on patreon.com/RatioBG again. And I think that should be it. Well, again, you can follow us on all social media, and you can check our website to check everything that we are currently doing and that we've been doing in the past. I think that should conclude everything that I had to say. So, ladies and gentlemen, thank you once again for joining us tonight. I hope you learned a lot today, and I promise you will learn a lot on our next event as well. Thanks again to the European Space Agency. Thanks again to my colleagues and to all the people who made this program possible. So, thank you very much, and I'll see you next time. Bye-bye.